This is VLSI data conversion circuits, lecture 22. In the last class we were wondering what would happen to a delta sigma modulator where we have a loop filter, a specific example being something like this going into a quantizer. We close the negative feedback loop around this. This input signal is denoted by U, the output of the quantizer is denoted by V, and the output of the loop filter is denoted by 1. Now, if we assume that this quantizer here behaves like an additive noise source, then the Z transform of the sequence Y was calculated to be what? So, we said V was U plus, or rather V was nothing but STF times U plus NTF times E, where E is the quantization noise, okay, and this is approximately 1, which means that V is U plus NTF times E. I am omitting the Z's all over the place, and therefore the signal at the input to the quantizer Y will be given by U plus NTF minus 1 into E, right, all right. In the last class we were wondering, of course this is all nice if the quantizer is indeed an additive noise source. However, a practical quantizer, apart from being horribly nonlinear, also will have saturation. The levels, I mean, if you go on increasing the analog input, the output is not going to keep increasing. In other words, the staircase has got some limits, and we were trying to see what would happen to the behavior of the delta sigma loop if the quantizer saturates, right. And I mean, given that this is a nonlinear system with feedback, the analysis if done rigorously would be pretty difficult to do given its nonlinear also. So, we resort to some techniques where you try and approximate the nonlinear characteristic or a nonlinear system by a so called best cut linear system. Then we assume that okay, we have spent a lot of time learning linear stuff, so we might as well apply all that theory to this so called linear system, which is by definition a close whatever relative of the corresponding nonlinear network. So, this kind of analysis, which has its origins in the early 50s, is what is called describing function analysis, where the basic idea is to replace a nonlinear system with an equivalent linear system. Of course, one must bear in mind that whenever one tries to do things like this, there will always be cases where it does not work out at all, right. So, this is not a bulletproof way of analyzing this, but it gives us many insights to system operation, right, and allows us to make at least the right direction of design choices and helps us gain intuition about how this whole loop works. To get exact results, of course, one would resort to computer simulations, which in this day and age is pretty straightforward and simple to do, right. So we will not get into the nitty gritty of finding the describing function and analytically and using it to find stability criteria and all this stuff. Okay. What we are going to do instead is to give give ourselves an idea of this whole process, and most importantly develop intuition about A, why the modulator becomes unstable, right, and B, changing these parameters in some direction. For example, one might decide that you increase the number of levels in the quantizer, right. One would naturally be worried about, or rather curious about, what this does to the stability of the loop, right. These are normal trade offs. For example, you increase the number of levels in the quantizer, you choose a higher order, right, things like that, which are design parameters or design choices, and we would like to understand how choosing one of these things influences the stability of the loop and what the trade offs are, right. So to that end, the last time around we took a second order delta sigma modulator with 7 levels. What was it, 7 levels, or the levels were -7 through 8 level quantizer, right. So delta was 2 and the number of levels n was 8. So they go all the way from -7, -5 all the way up to 5 and 7. When the input to the modulator is made to be well within the quantizer range, right, we see that the red curve here or the red sequence here denotes the modulator output, that is V, all right, and the blue one here is, it is not Y. Please recall from the discussion we had in last class that the Y can be decomposed into the YDC plus N1, right, and given that YDC plus N1 is incident on this nonlinear device, we try to approximate this to a linear system by finding K1 and K2 such that you minimize the error V minus K1 times Y dc minus K2 times N1, you minimize the average squared error, right, that is the best you can do. In other words, you try to choose K1 and K2 intelligently such that the error between a linear approximation and this nonlinear device is as small as possible. Obviously the fit will not be, when you try and attempt to do this, you will find that the error is not 0, right, the error would only be 0 if the box was a linear system, correct. So this happens to be the error waveform, and if the input plus the quantization noise, that is YDC plus N1, lies well within the quantizer range, it should come as no surprise that the mean square value of the error must be delta square by 12, going through, going by the original arguments that we had about if the input is busy and then the quantization error is uniform, and in which case its mean square value will be delta square by 12, right. So it indeed turns out that this mean square error happens to be about 1/3, which is delta square by 12. Okay, so this is not surprising. Then what do? I will increase the input amplitude, or rather increase the DC value such that for the same modulator I have doubled the input. Please recall that the maximum level is plus 7, right. So the input is 6.28 in this case, and on top of it there is some shaped quantization noise riding over this DC input, right, which now means that the quantizer will saturate, and seems like that is happening quite often, as you can see in this picture, right. So, if the quantizer saturates, we see couple of things happening. This is V, this is Y, I am sorry, this is not Y, this is K1 times Y dc plus K2 times N1, and since we are now saturating the quantizer, right, it makes sense that we are not able to fit this quite as nicely as we were able to fit it during the, I mean in that region where the staircase had a gain of 1 for both the noise and the DC component, alright, and that does come out in the math. The gain for the signal is close to 1, right. This is again not too surprising, because as far as the input signal is concerned, it is still within the linear range of the quantizer, right. However, the gain for the noise is now significantly lower. What was close to 1 is now dropped to 0.5. So, this is the noise gain, and we also see that the mean square value of the error has increased from delta square by 12, which was 1/3, to something which is about 30% higher. This also makes sense, because please recall that the error of the quantizer is only bounded when the input is within the linear range of the quantizer, correct. So, if you plot the quantizer error transfer curve, it is some sawtooth kind of waveform within the quantizer range. Beyond the quantizer range, it will eventually go to infinity, you understand. So, the quantization error transfer curve will probably look like this, and right now the input is sitting somewhere here, on top of it there is quantization noise riding. So, you can see that when the quantization noise really starts to become large, right, the shaped quantization noise, you will easily excite some part of the characteristic where the error is large. So, it makes intuitive sense that the mean square value has gone up from delta square by 12, right. But the key point is to notice that the noise gain has dropped, and dropped quite dramatically, correct. And intuitively this makes sense, because I mean the noise is now saturating the quantizer, and when the quantizer is saturated, there is really no connection between, there is no resemblance between the output waveform and the input waveform, okay. So, it is almost like the noise is not coming out at all, which on average terms means that the gain has come down. Does this make sense? Alright. Now, let me up the ante a little bit and increase the DC input to from 6.3 to about 6.5, and this must only make things even worse for the noise, correct. And again, as you can see, this is V, this is K1 into Y dc plus K2 into N1, and this is the error, and you can see that the mean square value of the error has gone up a little bit, but the most significant thing that you must notice is that the gain for the noise has gone down even further, right. In other words, a small change in the DC value close to the linear range of the quantizer is enough to push the gain for the quantization noise down dramatically. What was 1, okay, can fall down, in this case as we see, has gone down to 0.26 or so, you understand. Okay. So, the question now is, what happens Well, I mean this I would suspect is simply numerical, and I mean it is not a significant effect. I think it is still close to 1, right. Pardon?
If you keep on increasing YDC, I mean then this K1 will also come down, right?
Eventually, yeah. So I suspect what is happening is that this input is close to 6 point something, right, and the output now stays mostly at 7. So it appears as if some slight increase. That's all. So I don't think this 1.025 is a significant.
So this gain K2 will come down even when we decrease YDC very low, right?
Of course.
Because
So
saturation is on the both
that's good. That's a good point. So what he's pointing out is that even when the quantizer saturates towards the negative side, the same thing must happen. Correct? Okay, great. Now let's see what happens now when you have a high order loop filter. Please note that the motivation for this discussion was the following. We found that 1 minus Z inverse was giving us good invariant SQNR. Then we got greedy and said we put 1 minus Z inverse the whole square, it was getting better. Then we said, hey, why not 1 minus Z to the minus 3, I mean 1 minus Z inverse the whole cube, or 4 or 5 or 6. Okay. So in other words, we would like to make this L of Z have as high a gain at DC as possible and roll off, you know, at as 1 by omega cube for small frequencies. Then you will expect to get a noise transfer function which is 1 minus Z inverse the whole cube, right. So in general, given an NTF, we can always go and find L of Z using 1 by 1 plus L of Z gives the NTF, alright. And now what is happening, as we discussed in the last class, this system can be broken up into 2 as far as analysis of stability is concerned, right. If you do not like to think about it as 2 systems, you can always think of the input as being, given our background in analog, right, as the input as being the quiescent value and replace everything in the loop by its incremental equivalent, correct. So then we have the loop filter, so the quiescent value becomes 0, right. So you can think of this as the incremental picture of the entire loop, okay, given that the quantizer is non-linear. The only thing we need to worry about is, instead of having a quantizer, we have a gain K2 plus some fitting error E, and this feeds back, right. So the true transfer function or the poles of this loop are given by the roots of what equation? 1 plus L of Z times K2 equal to 0. So clearly K2 influences the locations of the poles and can therefore influence the stability of the loop, because stability is all, I mean you want to make sure that the closed loop poles stay within the unit circle if you want a stable system. Does this make sense? All right. So I did an experiment. I chose the NTF to be 1 minus Z inverse the whole cube, from which I found L of Z, right, which means what is L of Z? 1 by 1 minus Z inverse the whole cube minus 1, all right. And then, given that I know L of Z, I can go and find the roots as K2 is changing from 1 to 0, correct. I mean K2 equal to 1 corresponds to what? Corresponds to the modulator being in that uniform staircase region, right, and as the input signal gets closer and closer to the saturation limit, K2 will fall, right. So we plot the locus of the poles of the system which are the roots of 1 plus K2 times L of z as K2 varies from 1 to 0, right, and I have done that experiment for you. I hope you are able to see this, all right. So the shown here is the unit circle. For k equal to 1, where are the poles? Where do you think the poles are? I mean when k equal to 0, the closed loop system has a transfer function of 1 minus z inverse the whole cube, right, which is nothing but z minus 1 the whole cube divided by z cube. So all the 3 poles will be at the origin. So this corresponds to k equal to 1, okay, and as K2 keeps increasing, I mean as K2 keeps falling, what happens is that the poles, you must realize that 2 of them will be complex conjugate, right, which means the poles must, I mean if on top there is a pole, there is a corresponding pole in the lower half, and as you can see as k keeps falling at some critical value of k, they cross the unit circle, therefore causing the system to become unstable, okay. So one pole remains inside, but these complex conjugate poles keep moving towards the unit circle as k falls down, and for some critical value of k they cross the unit circle, beyond that they actually get out of the unit circle, which means that the impulse response corresponding to those pole locations is a sequence which grows exponentially. Is this clear? All right. So let us see what that value of k is. So what I did was plot the magnitude. So this is the magnitude of the largest pole, okay, as a function of k. When k equal to 1, what should the magnitude of the poles be? 0, right, that makes sense. So as k keeps falling, you can see that the magnitude of the poles keeps increasing, and what is the critical value of k at which the system becomes unstable? When the magnitude of the pole becomes equal to 1, and that happens around around 0.5 or so. Is this clear? So what we see is that once the quantizer gain falls below 0.5, if we attempt to realize a noise transfer function of the form 1 minus z inverse the whole cube, you will find that the modulator becomes unstable. In other words, the input to the quantizer will simply blow up, all right, because the impulse response now has got components which do not die down at all with time, which means that the input to the quantizer will blow up. I mean you should not be tempted to conclude that the system is stable by looking at the output of the quantizer. You understand? The output of the quantizer will always be bounded because it is saturating from at -7 and +7. You have to look at the input to the quantizer and make sure that none of the state variables inside the system actually blow up to infinity. Is this clear? So, this explains the signal dependent stability of the modulator. So, this is a third order root locus example. I also did that for a second order delta sigma loop. Again, what corresponds to the NTF is 1 minus z inverse the whole square. So, for K2 equal to 1, where are the poles located? At K2 equal to 1, the poles are located here, and as K2 keeps falling, we see that the poles do indeed move, right, but you can always see that they are within the unit circle. Okay. All right. All right. This is somewhat analogous to, you know that whenever you have a second order system, all right, regardless of the value of the gain in continuous time systems, you see that the poles will always lie in the left half S plane, right, and I mean they will never get into the right half part. So, this is a somewhat similar result. Okay, regardless of what K2 you have, the poles will move, but they are always sitting inside the unit circle. All right. So, what happens? The question is what happens to the input of the quantizer when the input exceeds a certain level, and what will happen is that the input to the quantizer will become very, very large, and I mean the entire noise shaping property of the loop is lost. Okay. So, in other words, signal dependent stability is something that one has to expect with this kind of system. All right. So, in other words, this nice property of the in-band noise being very small can only be achieved when the quantizer does not saturate. All right. In other words, the input to the quantizer always lies within this range. Okay. But please note that the input to the quantizer and the input to be digitized are two different things, right. One is y, the other is u. So, if y has to be restricted to the range of the quantizer, it follows that u must be pardon?
YDC plus N1 should be lower than the, it should lie in the range of the
quantizer. So, what conclusion can you make about u?
Less than the maximum. Less than the
So, clearly if this is the range of the quantizer, right, the input cannot be cannot occupy the full range of the quantizer, it must be smaller by some amount, right, because you must leave some range for the shaped quantization noise to wiggle or ride over the input. Okay. So, this is the, let us say pictorially, this is the stable input range okay. So, the ratio of the stable range of inputs to the quantizer range itself is often called the MSA or the maximum stable amplitude. Okay. Now, given that we have this intuition, let us try and figure out what would happen if we went on making the noise transfer function more and more aggressive, in the sense that we started off with 1 minus z inverse, then 1 minus z inverse the whole square, now we go to 1 minus z inverse the whole cube, and in this process what do you think is what do you think will happen to the maximum stable amplitude? It will decrease, and why does that make sense? So, as the order of the noise shaping goes on increasing, we see that the gain at out of band frequencies, that is the gain at omega equal to pi, is going on increasing by a factor of 2 every time, right, which means that the variance of the noise riding over the input signal is going on increasing. If the variance of the noise increases, then what will happen? The probability of saturating the quantizer is higher, which means that even if the input is small, right, because of this lot of noise shaping going on, we see that the shaped quantization noise is going to saturate the quantizer, thereby causing the loop to become unstable. So, as you go on increasing the order of the noise transfer function, if we did not do anything, if we made the noise transfer function 1 minus z inverse to the power n, right, we will see that the maximum stable amplitude will be a very small fraction of the quantizer input range, because you have to accommodate now the increased variance of the shaped quantization noise, correct. And the shaped quantization noise and all these assumptions make sense when you are starting from within the middle of the quantizer and keep going up, because as long as you do not hit the saturation limits, right, the quantizer can be pretty much thought of as a additive noise source. It is only once you start saturating the quantizer that the gain for the noise becomes smaller than 1, and if the loop filter is of high order, which is what it would be if you want to realize 1 minus z inverse to the n, then the quantizer effective gain for noise becomes smaller, causing the noise variance to increase, causing the quantizer to saturate even more, and this is like a regenerative process which will cause the input to the quantizer to suddenly blow up in magnitude. Does it make sense? So, this is why it is not, one cannot go on making n larger and larger and larger. You understand? Couple of points that I would like to make here. Does somebody have a question? Okay. So, couple of points I would like to make here. What do you, I mean, one thing is, okay, we are going to make this system, right, we understand that there is a maximum stable range, a maximum stable amplitude. Let us say my input is beyond the maximum stable amplitude, right. So, clearly the system becomes unstable, the input to the quantizer just blows up. After this, let us say I bring my amplitude down to within the stable range, or let me just say, to make matters simple, let me say I just simply make the input 0. So, the input, I started from 0, I went on increasing it, beyond a certain point the modulator becomes unstable, and the state variables inside my loop filter become unbounded or become very, very large. Then I realize that something is wrong, and suddenly say enough is enough, and I ground the input, so that the input is now technically within the stable range of the modulator. What do you think will happen? Do you think the modulator will continue to oscillate, or do you think it will come back given the inputs are? Pardon? Okay, the input was 0 first, right. So, this is well within the linear range of the quantizer. So, I go on increasing the input, eventually the amplitude will become large enough that it exceeds the maximum stable amplitude, then the loop becomes unstable, and therefore, the state variables inside the loop, which basically are the voltage levels, or the values inside L of z, start to blow up. Then I immediately sense something is wrong and make the input 0, which is clearly within the within the quantizer range. Now the question is, what do you think happens? Why?
Because of negative feedback.
Okay, it so turns out that for a second order modulator, things do indeed come back, and the intuition goes like this. So, when the modulator is unstable, the internal state variables are very high, so the quantizer is saturating like anything, correct, which means that the effective gain of the quantizer for this quantization noise is, it's very, very small. So, in other words, the poles are somewhere around here. You understand, this is the root locus for a second order modulator, as the gain starts from 1 and keeps falling down to not 0 in this case, I think it is 0.1, but never mind, right. So, the poles are still within the unit circle. Now, think of the situation as the following: we have a system whose poles are within the unit circle, and you start off the state variables at some very large values, and the input is 0. So, if you have a stable system with initial conditions being very large, right, but the system is stable and the input is 0, what will eventually happen to the states? They will eventually die out, correct. So, for a second order modulator, right, if the input was such that it pushed the modulator for a little time outside its the region where it is stable, and then the input was brought back or made 0 for example, then what would happen? We see that we are somewhere here, you can think of it as starting off here, and then these states will tend to decrease in magnitude because the poles are within the unit circle, correct, and as the states decrease, eventually you will come to a situation where you stop, or you reduce the degree to which you saturate the quantizer, which means that the gain goes on increasing. So, you come back along this curve and you are still okay, alright. Unfortunately, that is not true when you have a higher order modulator, because the intuition Of course, the whole process is extremely nonlinear and very complicated, right. So, all that we can do is get some intuition about why things happen the way they do, all right. So, I will in one of your homeworks you will do this and convince yourselves that this is indeed true. In a third order modulator, for example, when the modulators become unstable, the variance of the quantization noise, or rather the input to the quantizer becomes so large that you are deep inside the in the unstable region, that is way outside the unit circle, and making the input 0 does not really help, because you are still outside the unit circle and these state variables have are still growing exponentially. So, you will find that modulators with order 3 and higher, correct, will become unstable beyond their within quotes linear range or stable range, and more importantly it is not straightforward to make them stable again by bringing the input back to within the stable range. Okay, you have to do something more, all right. And one common thing that is done in products is to simply zap the state variables. I mean, the problem is that now earlier the problem was that the input was too high and was causing everything to oscillate and causing the state variables to become very large. It is very easily detected in practice. When the modulators become unstable, right, one thing to do is just check the input to the quantizer. If it has become very large, then you know that the modulator is unstable, and you can bring it back into the stable region by A, making sure that the input does not exceed the maximum stable amplitude, and 2, you bring the state variables back to sane levels, and the easiest thing to do is to simply make them all 0, right. So, you can detect when the modulator has gone unstable, right, and reset all the states, and you start off all over again, you understand. So, amplitude induced oscillations which do not go away once the input amplitude has gone down is a characteristic of nonlinear systems. It is not just observed in delta sigma modulator loops, but also in continuous time systems where it is a property of nonlinear systems, that is all. So, you can have these systems lock into nonlinear oscillations. They have been triggered by some input, and then even after the input goes away, the oscillations continue, you understand. So, the summary of the whole thing is that a delta sigma loop is only stable for input signal range which is a part of the quantizer range. It cannot be the entire quantizer range, and the reason for that is that the true input to the quantizer is the input to the modulator plus shaped quantization noise, and the loop is becoming unstable because the quantizer is saturating, correct. So, anything that you do, right, which will increase the variance of the shaped quantization noise is bound to result in a reduced maximum stable amplitude, correct, because the input to the quantizer has to accommodate the shaped noise plus the input. It makes sense that, I mean, increasing the order of the loop 1 minus e inverse to the n, for example, will dramatically increase the variance of the shaped quantization noise, which will then therefore make the maximum stable amplitude is smaller. Is this clear? Okay. So, we are now in a situation where we have the following. we really like 1 minus z inverse to the n. Why do we really like it? The in band noise, I mean, is reduced by a large factor, correct, and we are getting, if you have 1 minus z inverse to the n, you get n plus half bits every time you double the OSR. So, seems like a really attractive thing. On the other hand, the maximum stable amplitude is very small, or keeps on reducing, and in practice becomes very small when you have when n becomes large. So, the question now is, what do we do to make, we want to have the best of both worlds, right. You certainly want to have 1 minus z inverse to the n, however, you want the maximum stable amplitude to be high also, correct. So, the question is, what do we do about this? You understand? So, let me quickly refresh your memory about finding the magnitude of a transfer function. Let us say you have a transfer function z minus p1 divided by z minus z1 divided by z minus p1, okay. How would you graphically determine the magnitude response evaluated at h of z? Sorry, what I meant to say was, how will you determine the magnitude response of h evaluated at z? Yeah, so of course you can plug in z into the formula and then find the ratio of complex numbers and this, but what I wanted to bring to your attention is the fact that if this is z, which is the point at which you need to evaluate the magnitude of this transfer function, what you can think of as, you can think of this process as finding the distance from z to all the poles, right, and you will get the magnitudes of those vectors, and you find the distance from z to all the zeros, and you find the magnitudes of those vectors, and find the ratios of the magnitudes of the vectors which go to zeros to the magnitude of the vectors that go to the poles, and that gives you the magnitude response, correct. And in our situation, we are pretty much interested in finding the magnitude of h of z or the NTF as we travel along the unit circle, correct. In other words, we are interested in evaluating h of e to the j omega, alright. So, what I wanted to point out is that when we have 1 minus z inverse the whole cube, what is happening? There are 3 poles at the origin, correct, the poles, and then there are 3 zeros at DC or z equal to 1, right. Now, when we plot the magnitude of the noise transfer function, all that we are doing is going along the circle, and for each point, at each point we are drawing these vectors from that point to the poles, that point to the zeros, and whatever, and plotting the finding the ratios. Please note that wherever you are on the unit circle, the distance from that point to the poles always remains, for this pole 0 constellation, the distance to the poles always remains the same, so that remains 1. At DC, this distance goes as is 0 at DC, and then starts to go as omega cube, right, and at omega equal to pi, what do you get? Each vector becomes 2, so 2 the whole cube becomes 8. So, in other words, the NTF kind of does something like this, alright. So, let me all right. This is 8. So, we need to, what we do not like, what is responsible for the modulator going into oscillation? Pardon? I mean, this is the problematic part, because as we saw the last time around, most of the contribution to the shape quantization noise is coming from high frequencies, that is frequencies in the neighborhood of omega equal to pi, right. So, this part of the NTF is something we like, that is giving us that omega to the 3. What we do not like is something, is the part of the characteristic at omega equal to pi. So, in the next class we see what we do to fix this problem and get 1 minus z inverse the whole cube as well as, pardon?
Because finally the problem is in the omega should be pi region.
Correct.
So like we have to decrease the gain in that region.
Correct. So, what does this do eventually? The whole modulator, what is it improving? It is going to increase the MSA. So, you can get the good noise shaping without losing too much on the MSA, right. So, we will see that the next class.